You thought you knew what was normal. A comet that orbits every 16.79 hours. It sounds boring. But when this comet comes from beyond our solar system, crossing 4.5 light years of emptiness and revealing the secrets of planets formed 13 billion years ago, boredom disappears. This is Tri Atlas, the third interstellar visitor, and its rotation over 16 hours has just shattered everything we thought we knew about deep space. On the morning of July 1st, 2025, in Rancola, Chile, the Atlas telescope, an emergency warning system for potential asteroid collisions, detected something moving against the backdrop of dense star fields of the galactic center. It moved not like our comets, too fast, too angled. The trajectory screamed, "This is not an asteroid." For several hours, astronomers around the world realized they had something unprecedented. The third confirmed macroscopic interstellar object passing through our solar system. But Atlas is not just a telescope. This is a global network of 4 robotic telescopes located in Hawaii, Chile, and South Africa. Each telescope scans almost the entire night sky every 24 hours, tracking objects near Earth that may pose a collision risk. The system processes over 100,000 images overnight. On July 1st, one of the images contained something unusual. A dim point of light moving at hyperbolic speed, exceeding the gravitational connection to the Sun. The remote Deep Random Survey Telescope in Chile, part of the Atlas network, recorded the first definitive detection. But the object was hiding in plain sight. The European Space Agency responded within hours, immediately deploying ground telescopes in Hawaii, Chile, and Australia. The NASA Office for Planetary Defense classified it as the third confirmed interstellar object, designated C2025 N1 Atlas, but Tri and Atlas were still hidden. Preliminary observations before the opening showed that he was filmed a few weeks earlier. The transitory Zwicky setup captured him on June 28th and 29th, with additional images taken from June 14th to 21st. Atlas had been tracking him since June 25th. Amateur astronomer Sam Dean found additional observations from Atlas dated June 5th. For nearly a month, this interstellar visitor had slipped past our instruments, remaining unnoticed. Why? He was passing right in front of the center of the galaxy, where millions of stars created a perfect camouflage cover. The Vera C. Rubin Observatory provided important data before the discovery, showing that Tri and Atlas were already active. On June 21st, 2025, its coma had an average diameter of 13,040 kilometers, about the same as Earth's. By July 2nd, the comet's coma expanded to 18,760 kilometers, a 10% increase in 11 days. This was unusual behavior for a comet, as they typically form their comas gradually as they approach the Sun. However, Tri and Atlas actively emitted gas at distances where most comets remain completely inactive. The first preliminary images showed something more alarming. The temporary Zwicky installation recorded Tri and Atlas on May 22, 2025. 6 weeks before the official opening, the object already displayed a noticeable, albeit vague, dome with a diameter of about 6,000 kilometers. On this date, Tri and Atlas were at a distance of 7.1 astronomical units from the Sun, farther than Jupiter. Most comets at such distances remain completely inactive. However, Tri and Atlas were already showing signs of significant degassing. The Institute of Astrophysics of the Canary Islands confirmed cometary activity using a 2-meter telescope at the TD Observatory on the opening day of July 1st. Many telescopes demonstrated that the coma had a distinct reddish hue, indicating similarity with dust components like those of II and Borisov. However, III and Atlas showed something unprecedented. The reddish hue intensified during July 2025 according to a study by Tony Santana Rosa and colleagues published in August. Common comets show a gradual change in color. III and Atlas changed drastically in just a few weeks. If you appreciate the documentary history of space exploration, this is the best way to support our work. Also, let us know which city you are listening from. This scenario is based on research and facts using sources from the journal Astronomy and Astrophysics, published on August 5th, 2025, as well as studies by Harvard professor A. Bilo's work on Medium, published in August 2025, including his analysis of properties with extreme negative polarization, which calls into question all existing comet models, and its discovery in August during the formation of an anti-solar tail. Additional sources include the archive preprint 25-07-14916 from July 2025, documenting the discovery of water ice in the coma using Gemini telescopes, South YEMOs, and spectroscopy, NASA, and RTF specs. Other sources include the SPRX discovery of a widespread coma of carbon dioxide reported in the journal Astrobiology in August 2025. Now let's return to the information. The numbers tell a story. Orbit and parabola. The speed was 14.3 kilometers per second relative to the local standard of rest. However, this number underestimates the actual speed. In relation to our Sun, Tri and Atlas move at a speed of 58 kilometers per second, fast enough to cross the diameter of Earth in less than 4 minutes. This speed means one thing. This object formed around another star. He was ejected from his star system and spent millions of years crossing interstellar space before reaching us. Orbital mechanics do not lie. The object known as Treshka and Atlas will never orbit our Sun. Its trajectory leads in a one-way direction through our solar system. The closest approach to the Sun will occur at the end of October 2025 at a distance of 4 astronomical units, just inside Mars's orbit. This is close enough for detailed study, yet far enough to avoid intense heating. Nevertheless, this object poses no threat to Earth. The closest approach to our planet will occur on December 19, 2025. At a distance of 8 astronomical units, which is approximately 269 million kilometers. The trajectory calculations showed astonishing accuracy. On October 3rd, the Treshka and Atlas will pass by Mars at a distance of 19/100ths of an astronomical unit, or 28 million kilometers. This is close enough for missions on Mars to observe it. The object will fly past on November 4th at a distance of 0.65 astronomical units, and then past Jupiter on March 16, 2026, at a distance of 0.36 astronomical units. Each encounter with the planet provides data on gravitational disturbances that help trace the object's origin in galactic space. However, the trajectory holds another secret. Reverse calculations of the orbital trajectory indicate that Treshka and Atlas have been traveling through interstellar space for about 4 million years. The calculations suggest that its origin is linked to a close flyby of a star that occurred when the first ancestors of humans began to master the use of tools. A cosmic wanderer, older than civilization, finally reaching our doorstep. Analysis of the orbital tilt shows that Treshka and Atlas are approaching us at an angle nearly perpendicular to the plane of the ecliptic, with a tilt of 62.4 degrees. This sharp angle indicates that the object originated outside the galactic disk, possibly from the thick disk population or ancient stars. Most interstellar objects should display random inclinations, but the trajectory of Treshka and Atlas indicates specific galactic sources dating back billions of years. Raúl de la Fuentes Marcos and his colleagues from the Gran Telescopio Canarias began intensive observations from July 2nd to 5. The telescope has a mirror of 10.4 meters, a spectrograph with a camera or series. They needed data on the rotation period. The initial studies could not identify them, but the resolution and light gathering power of the Hubble Space Telescope deciphered this task. The Hubble Space Telescope joined the observational campaign on August 20th, 2025. Hubble's measurements limited the core size to a range between 440 meters and 5.6 kilometers in diameter. The wide range reflects uncertainty in the composition and reflectivity of the surface. Darker surfaces appear larger at the same brightness. Highly reflective surfaces appear smaller. However, Hubble confirmed an important detail. The body named Tri and Atlas maintains constant variations in brightness that are precisely repeated every 16.89 hours. The Gemini South Telescope in Chile took stunning images during real-time educational observation sessions. Students could watch as the telescope tracked Tri and Atlas among the star fields. Images showed a distinct comet with a reddish hue, stretching nearly twice the diameter of Earth. Spectroscopic analysis during these sessions provided real-time data on its chemical composition. The spectrum revealed carbon-based molecules formed only in the extreme cold of interstellar space. But in September 2025, Gemini South captured something unprecedented. 3 and Atlas developed a visible tail structure. The tail stretched about 1 million kilometers, 7 times the diameter of Earth, pointing directly away from the Sun. However, there is one troubling detail. The tail shows the same variations in brightness as the core, with a period of 16.89 hours. The entire structure, nucleus, coma, and tail, rotates as a unified system. Nothing in comet science explains such behavior. The multi-object spectrograph Gemini captured the most impressive feature of the tail at the end of August 2025, anti-solar tail. Unlike a typical dust tail that points away from the Sun, This secondary tail extends towards the Sun, stretching about 200,000 kilometers in the opposite direction. Milov, published on August 27th, confirmed that this impossible geometry violates all known models of comet physics. 16.89 hours, plus or minus 0.23 hours. This number changes everything. You measure rotation by observing changes in brightness during the object's spin. 3 and Atlas demonstrate the amplitude of the light curve almost doubled. This means one side reflects significantly more light than the other. Such an extreme trick. The calculation of the rotation period requires capturing the object during several complete revolutions. GTC did just that. But what makes 16.89 hours frightening for traditional comet models? This is too slow for a normal comet nucleus, but too organized for a pile of loose debris. Most comet nuclei rotate every 6 to 18 hours, but they are bound by weak gravity and frozen volatiles. If you make them spin too fast, they break. If too slow, it requires extremely high structural integrity or something entirely different. Compare this to our previous interstellar visitors. Once, Oumuamua spun every 7.3 hours, fast enough to suggest it is a solid and dense object. 2 Borisovs rotated roughly every 24 hours, typical for loosely bound comets. But 3 and Atlas settled in the middle with 16 whole 89/100ths hours, not as fast as the Rokadenka, not as slowly as a fragile snowball. Something in between that challenges all our models. The comparison of the rotation reveals deeper mysteries. Oumuamua showed no coma, no degassing, nor any cometary activities. Astronomers discovered it only because sunlight was reflecting off its spinning surface. Borisov behaved like an ordinary comet, developing a coma and a bright tail as solar heat evaporated surface ice. But TRES and Atlas are doing something unprecedented. They maintain constant degassing, rotating with mechanical precision. The NASA Esperex Space Observatory recorded the most astonishing fact in mid-August 2025. TRES and Atlas have a cloud of carbon dioxide extending 348,000 kilometers in radius, almost the distance from Earth to the Moon. This cloud remains invisible to optical telescopes, but glows brightly in near-infrared wavelengths. The rotation period is 16 hours, meaning this massive gas cloud rotates as a rigid body. Challenging all comet behavior models, the data from SFE-RH revealed yet another anomaly. The carbon dioxide coma displays a complex internal structure with concentric layers separated by dark gaps. Each layer spans about 50,000 kilometers and rotates with the same period of 16 hours and 79 minutes. These structured layers suggest organized degassing considering specific surface characteristics, rather than uniform sublimation throughout the core. TRES and Atlas have a diameter of about 10 kilometers based on brightness and temperature models. For a core of 10 kilometers and a period of 16 hours and 79 minutes, this gives a surface rotation speed of approximately 1 meter per second. This is the minimum speed required for any ejection from the surface. Research at Harvard confirmed this in their records from August 2025. 1 meter per second. Slightly faster than a walk. The Gemini South Telescope spectroscopy from July 5th to 14th, 2025 revealed the mystery of the composition. The optical spectrum shows a red shift of about 10% per thousand angstroms, ranging from 0.5 to 0.8 microns, which exactly matches Type D asteroids, but at longer wavelengths. The near-infrared spectrum sharply levels to just 3% over 1,000 angstroms. This spectral behavior indicates the presence of large crystals of water ice in the coma, mixed with organic compounds. Modeling the spectrum requires 70% of meteorite material from Lake Tagish mixed with 30% of water ice to match observations. Lake Tagish is a primitive carbonaceous material that formed in the early solar system, but TRES and Atlas carry a train that originated from a completely different star system. The consequences of this astonish astronomers. Interstellar space preserves primordial chemistry over cosmic distances and millions of years. However, in August 2025, Tony Santana, Ross, and their colleagues published alarming observations. Comet Tri and Atlas were gradually becoming redder throughout July. This redness indicates a change in its surface composition, as the increase in solar heat activated various chemical components. Ordinary comets show similar evolution. But Trey and Atlas changed faster and more radically than any previously observed comet. Spectroscopy in the near-infrared range, conducted by NASA's IRTF observatory in July, detected strong absorption features of water ice in the range of 0 to 2.5 microns. However, The ice signatures show unusual temperature characteristics, suggesting the presence of subsurface reservoirs rather than just surface frost. It seems that water ice sublimates from several meters below the surface of the core, reaching the coma through cracks and vents controlled by a 16-hour rotation cycle. Ordinary comets develop comas, bright clouds of gas and dust. When solar heat evaporates surface ice, the ejected material usually moves much faster than the rotation of the surface. But Trey and Atlas challenge this model. Her coma extends for 26,424,700 kilometers, according to high-resolution images from GTC, which is twice the diameter of Earth. However, the ejection speed seems suspiciously low. A very large telescope of the European Southern Observatory provided important spectroscopic data using the Mustrum instrument in July 2025, discovering emission lines of carbon monoxide, cyanides, and hydroxyl radicals. Typical cometary chemistry. However, the width of the lines indicates that the gas is expanding at a mere 0.3 kilometers per second. Typical comets eject gas at speeds of 1 to 3 kilometers per second. Atlas is releasing material 10 times slower than expected. The Mars Express and ExoMars Trace Gas Orbiter from ESA observed Teary and Atlas during its approach to Mars on October 3rd, at a distance of 30 million kilometers. The high-resolution stereo camera of Mars Express and the CASES imaging system from ExoMars will photograph the comet from unique angles not accessible from Earth. The Omega and SPECAM spectrometers will analyze the composition of the coma from Mars orbit, providing stereometric measurements of the gas distribution around the nucleus. But the Parker Solar Probe mission offers the most exciting opportunity for a meeting. The spacecraft's trajectory in December 2025 will pass through the plasma tail of Tri and Atlas, about 0.8 astronomical units from the Sun. The instruments aboard Parker will directly show interstellar material, studying magnetic field interactions, plasma composition, and the properties of dust particles that cannot be determined through remote observations. NASA's exoplanet research satellite TESS has uncovered new mysteries. TESS observed the object named 3 and Atlas almost continuously from May 7 to June 2, 2025. Analyzing the accumulated images allowed for deep snapshots of the object. An astonishing result. 3 and Atlas were already showing cometary activity at a distance of 6.4 astronomical units from the Sun. 2 months before the opening, at a distance of 6.4 astronomical units, the object showed signs of coma formation even beyond Jupiter's orbit. Most comets become active only when crossing the orbit of Mars at about 1.5 astronomical units. Water effectively sublimates only within the inner part of the solar system. However, Tri and Atlas exhibited activity at temperatures where water remains frozen. What could cause such activity? TESS's data revealed something unprecedented. Tri and Atlas demonstrated brightness changes while remaining stable even before its discovery. The same rotation period, lasting 16.79 hours, observed in July 2025, had already been captured in images by TESS in May. This object had been continuously rotating for months before its existence became known. High precision indicates a more organized internal structure than typical cometary fragments. Measurements of the angular diameter obtained from ground observations in July 2025 show that the visible coma spans about 2 angular seconds in width at half height, expanding to 10 angular seconds at the faint outer edges. However, the carbon dioxide shell detected by the spectrometer extends far beyond the visible coma, creating a massive invisible atmosphere around the core. The rotation period pertains to both visible and invisible components, indicating they move together as a single system. However, polarimetric observations revealed the most troubling anomaly. The analysis conducted by Abalov in September 2025 showed that Tri and Atlas exhibit extreme negative polarization, with light-scattering properties never before observed in any object of the solar system. The degree of polarization reaches -15% at phase angles around 100 degrees. Ordinary comets show positive polarization under similar conditions. Negative values indicate properties of dust particles that cannot form under solar system conditions. Data on polarization suggests that Tri and Atlas contain dust particles with reflection coefficients and size distributions completely uncharacteristic of our cosmic neighborhood. The particles found in the composition are metallic submicron elements with optical properties resembling processed metals rather than natural silicate or organic compounds. This composition does not match any known comets, asteroids, or meteoroids in our solar system. The answer was obtained using the James Webb Space Telescope as a result of observations made at the end of August 2025. The object named 3 and Atlas turned out to be extraordinarily rich in carbon dioxide compared to the comets of the solar system. Carbon dioxide sublimates at significantly lower temperatures than water ice. Yet even carbon dioxide should not cause significant activity at a distance of 6.4 astronomical units. This is only possible if the core has an extremely high surface-to-volume ratio or an unusual composition. Observations made with a near-infrared spectrograph at a distance of 3.3 astronomical units demonstrated something unprecedented in comet science. 3 and Atlas shows enhanced carbon dioxide degassing, especially towards the sun. This directed degassing leads to the formation of an asymmetric coma that rotates with the nucleus every 16.79 hours. Ordinary comets exhibit a more uniform distribution of degassing across their surface. 3 and Atlas behaves as if he has active regions that periodically turn on and off with mechanical regularity. The spectral analysis of carbon dioxide revealed the presence of water, carbon monoxide, carbonyl sulfide, ice crystals, and dust, alongside the dominant signal of carbon dioxide. However, the proportions of these substances do not match the normal composition of a comet. Carbon dioxide dominates in a ratio never before observed in the comets of the solar system, with a carbon dioxide to water ratio exceeding 10 to 1, directly opposite the typical chemistry of comets where water predominates in similar proportions. But the analysis of carbon dioxide also revealed the most striking detail in the spectroscopy conducted at the end of August. The instrument recorded emission lines of aldehydes with intensities indicating production rates of over 1,000 kilograms per second. Formaldehyde is formed from the decomposition of methanol under specific temperature and radiation conditions. However, the temperatures required for effective production of formaldehyde do not exist at the distance of Tri and Atlas from the sun. The mechanism causing such mass degassing of formaldehyde remains completely unexplained. Observations in the mid-infrared range also recorded thermal emissions of dust particles throughout the area, with temperatures ranging from 50 to 120 kelvins. These temperatures are too high for thermal emission equilibrium at the solar distance of Theia and Atlas. Dust must be heated by internal energy sources or exotic chemical processes disrupting standard thermodynamics for small bodies in the solar system. This leads us to the rotation anomaly. 16 hours and 47 minutes indicate an object with very high density or something with an internal structure that we cannot understand. Asteroids of the reusable debris type usually spin much faster when they are small, or significantly slower when they are barely held together. 3 and Atlas are somewhere in between. A spectroscopy campaign conducted by the Very Large Telescope revealed the most troubling details at the end of August 2025. The high-resolution spectrograph of the PLT telescope detected atomic nickel in the coma, which is not unusual for comets, but Tri and Atlas show strong nickel emission lines with almost no detection of iron. Every natural object in the solar system contains nickel and iron together, as they form as alloys in the cores of stars and during the differentiation of planets. Pure nickel without iron violates the fundamental principles of cosmic chemistry. The analysis of VLT data conducted by Abeloev and published on August 29th highlighted this anomaly. The ratio of nickel to iron in Tri and Atlas exceeds 100 to 1 based on the intensity of spectral lines, unlike meteorites. Ordinary asteroids and comets show a nickel to iron ratio from 0.01 to 0.01. 3 and Atlas break all the rules of natural cosmic chemistry. The rotation period of 16 hours remains constant as this impossible chemistry spins through space. The detection of cyanide adds another layer of mystery. VLT spectroscopy shows that the emission lines of CN sharply increase as Trix and Atlas approach the sun. The production rate doubles every 0.2 astronomical units of proximity. This sharp gradient indicates subsurface reservoirs of hydrogen cyanide precursors that are thermally activated. However, a periodicity of 16 hours and 47 minutes is also observed in the emission of cyanide. The gas release pulses along with the rotation. The X-shooter VLT spectrograph detected emission lines of forbidden oxygen at 6,306 and 6,364 angstroms with unprecedented intensity for a comet. These lines are formed only in gas with extremely low density, subjected to intense ultraviolet radiation. The emission rates suggest gas densities 10 times lower than those in ordinary comets, but they are subjected to levels of ultraviolet flux that should not exist at their current distance from the Sun for Tri and Atlas. The detection of nickel has sparked speculation about its artificial origin. Pure metallic nickel requires industrial processing or exotic astrophysical conditions. No known natural process creates nickel without iron in environments similar to comets. Some researchers suggested that Tri and Atlas could represent technological waste from another civilization. However, the tool's limitations prevent definitive conclusions about the purity of nickel. But the increase in brightness recorded in mid-September 2025 added another mystery. Observations from Earth showed that Comet Tri and Atlas were illuminating much faster than standard comet models predicted. The brightness increased by almost half a magnitude in just 1 week. Ordinary comets show a gradual increase in brightness as they approach the Sun. However, Tri and Atlas suddenly shone as if someone had flipped a switch. The increase in brightness coincided with the discovery of numerous jets of dust emerging from the surface of the core. High-quality images from the Takana Large Millimeter Array showed at least 7 distinct jets directed at specific angles relative to the axis of rotation. Each jet turned on and off with precise synchronization, linked to a rotation period of 16 hours and 47 minutes. Such organized behavior of jets had never been observed in other comets in the solar system. The analysis of the visible spectrum using the GTZ observatory reveals another clue. 3 and Atlas reflect light with a slight reddish tint, similar to D-type asteroids. D-type objects are primitive, rich in organic compounds, and inhabit the remote corners of the solar system. However, Tri and Atlas exhibit spectral signs of both type D and previous interstellar objects, such as Odin and Oumuamua, and II, and Borisov. The reddish hue indicates the presence of complex organic molecules, carbon chains forming in the cold interstellar space. Here, the rotation period of 16 hours and 47 minutes becomes critically important for theories of origin. If Tri and Atlas formed in the outer regions of their home planetary system, they could have experienced conditions similar to those in our Kuiper belt. Objects in this belt rotate depending on their formation history, how they accumulated, collided, and survived through selection. The rotation period captures this history. Computer simulations of planet formation predict that small bodies are ejected into interstellar space during the evolution of the system. In the early stages of violence, more objects are expelled. The ejected population carries traces of its native environment. Tri and Atlas may be a relic of planet formation that occurred during the cosmic midday, the most active period of star formation in the universe about 10 billion years ago. Modeling thermal processes becomes critically important considering the 16-hour rotation period. Solar heating oscillates sinusoidally as different areas of the surface face the Sun. However, thermal inertia, the speed at which a material responds to temperature changes, depends on the subsurface structure. Tri and Atlas demonstrate thermal behavior consistent with low thermal inertia, indicating a porous or spongy subsurface layer. Nevertheless, this contradicts the structural integrity implied by stable rotation. Sublimation analysis shows that ice crystals form far from the core's surface. The James Webb Observatory detected traces of ice at a distance of 4 to 10,000 kilometers from the core center. This indicates that water ice crystals are ejected due to the degassing of carbon dioxide and then sublimate in the vacuum of space. The rotation period, lasting 16 hours and 47 minutes, regulates this process, as the ventilation of carbon dioxide occurs mainly in certain areas of the surface. However, attempts to conduct ground radio observations using the observatory in Puerto Rico and the Deep Space Station network completely failed. Radio signals indicated that the objects Tri and Atlas have an extremely low visible density, lower than that of water. Objects with such low density should be structures of debris barely holding together. However, Tri and Atlas demonstrate precise rotation and coordinated degassing patterns, which requires a sturdy structure. The failure of radio observations implies that Tri and Atlas possess unusual electromagnetic properties that hinder effective reflection of radio waves. Ordinary rocky or loose objects produce strong radio signals proportional to their size and density. Tri and Atlas appear transparent to radio waves, indicating an extremely low density or exotic material composition that does not interact with electromagnetic radiation in the expected manner. Modeling based on gravity data, R3 attempted to trace Tri and Atlas back through galactic space. Calculations show that the objects could have originated in a star system that passed within 50 light-years of our solar system around 4 million years ago. However, uncertainties in galactic motion make it impossible to accurately identify the source. The analysis of star associations shows that 3 and Atlas likely originate from a metal-poor stellar population formed in the first billion years of the universe's existence. The stars of the second population have a chemical composition different from the Sun, leading to planetary systems with exotic material properties not found in our solar environment, explaining unusual iron ratios and other chemical anomalies. A rotation period of 16 hours imposes limitations on the internal structure through mathematical analysis. Assuming that 3 and Atlas represent a liquid body without resistance, it would break apart under centrifugal force if its density did not exceed about 200 kilograms per cubic meter. This constitutes 1/5 the density of water possible for a mixture of ice and loosely bound rock. However, mass loss calculations based on observations of the comet show that Comet Tri and Atlas sheds about 15 kilograms of material per second during peak activity near perihelion. Throughout its journey through the inner part of the solar system, the object will lose about 2 million kilograms, which may constitute about 2% of its total mass, assuming its core is about a kilometer in size. This gradual erosion does not significantly affect the rotation period, as the material mainly comes from the surface layers. But the analysis of dust particles revealed another mystery. Microscopic particles in the coma demonstrate crystalline structures that form only at temperatures above 800 Kelvin, hot enough to melt aluminum. These high-temperature crystals could not have formed in the cold interstellar medium or in the outer solar system, where Tri and Atlas are now located. The particles likely formed near the parent star and then preserved their structure during millions of years of interstellar travel. The brightness and stable level of activity observed during the approach to perihelion confirm an unusual structure. Most comets exhibit brightness bursts when their nucleus is exposed or large chunks break off, but Tri and Atlas remain surprisingly stable. The rotation period is 16 hours and 47 minutes, which is predictable and almost resembles design. October 30th, 2025 marked the perihelion, the closest approach to the Sun at a distance of 4 astronomical units, far enough to avoid intense heating, but close enough for detailed observations. Ground telescopes and space missions coordinated the most intensive study of any interstellar object. However, the 16-hour rotation period has already revealed the key to understanding. 3 and Atlas do not behave like a typical comet. He behaves like something else, maintaining structural integrity over millions of years of interstellar travel, rotating with mechanical precision. There are possibilities for encounters with spacecraft, but they require perfect synchronization. The Solar Orbiter mission of the European Space Agency may potentially cross the tails of Comet Tri and Atlas during its solar approach in February 2026. The tails of plasma, dust, and neutral particles extend for millions of kilometers behind the nucleus. Even a distant intersection of a tail can provide direct samples of interstellar material. The Bepi Colombo mission, aimed at Mercury, offers another opportunity for encounter.